When I was a child, I loved to play with loudspeakers. It was especially a must for me to push against the dome at the middle of the paper diaphragm. Once you push it, it didn't come back, but the speaker would still work. And my father completely freaked out when he first saw what I had done all the speakers at home. I was dying to know that how could possibly a sound come from a paper diaphragm? And what was hiding behind it was a complete mystery for me. What I didn't know at that time was the sound was actually made by a light inductor, which was so light such that even a tiny wave of current could make it vibrate. Then when the paper diaphragm vibrates along with the inductor, it also vibrates the surrounding air so that we can hear the sound of the music. Here is a simple model of a loudspeaker. The diaphragm here that is connected to an inductor coil which is free to move in the vertical direction above a permanent magnet which has a very powerful and constant magnetic field. When current passes through this coil, it actually induces its own magnetic field which is changing like that current and interacts with the magnetic field of the permanent magnet that creates a force on the diaphragm. Through the Lorentz force equation, let me write that down. F equals E plus V, the speed of the charge, cross B. So we see that the force by the Lorentz law will act on the charge in the coil by the magnetic field of the permanent magnet and the changing magnetic field that is actually induced by those charges themselves. Indeed, the entire characteristics of a loudspeaker depends on complicated mechanical and acoustic dynamics. We can still consider it as a simple inductor, at least by means of an electrical perspective. So if we want to wind our own coil, we have to choose the wire to be thin as much as it can. I found a 0.05 millimeters of wire which is a suitable candidate to use as a speaker coil. The winding process of this wire is a painstaking process and may need a couple of trials before obtaining a good-looking coil. The number of turns is very important in terms of the performance since it determines how powerful the magnetic field even if a small current passes through. For example, if you have 30 turns and your current on the wire is just 100 milliamps, you will get a magnetic field strength as high as the magnetic field strength of a 3 amperes of current on a straight wire. You can simply multiply the number of turns with the current passing through the coil since the current is responsible from the creation of the magnetic field. Now, securing the coil on a piece of tape is a must since the wire is so thin and it can get messed up quickly. To strip the insulating cover around the wire, choosing to burn it up with a lighter is a safety approach since the wire can easily break using sandpaper. To feed the coil, I wanted to use a tiny 2 watts audio amplifier and wasn't able to make it work. Unfortunately, this silly amplifier can't even produce 2 watts and can't drive the coil. Speakers need powerful and broad-range amplifiers to be driven efficiently, which is a task that is way more advanced than a tiny amplifier can accomplish. Therefore, we have to a little bit further investigate into the theory of inductors and why is my voice still echoing? So we simply know that the voltage across an inductor is L didt. Imagine our current through this coil is a sinusoidal waveform, a very simple one, as IL of t equals I0 sine omega t plus theta I. Here theta I is my phase angle of the current and omega is the frequency of the sound wave. According to this relationship, we can take the derivative of the current with respect to time and multiply by the inductance of the coil. We will get the voltage waveform with respect to time as I0 L omega cosine omega t theta I. But we are not satisfied with this expression and let's write that as a sine wave which will be I0 L omega sine omega t plus theta I minus pi over 2. So as you can see, there is pi over 2 phase difference between the voltage and current. Simply voltage leads current by 90 degrees out of phase when there's an inductor. And let's also write this in terms of complex numbers. That means VL of t, J I0 L omega sine omega t plus theta I. Now we can also calculate the impedance of the coil by using our old Ohm's law, which tells us that the impedance of the coil is simply VL over IL, that is J I0 L omega sine omega t over I0 sine omega t plus theta I. Now cancelling the I0s, cancelling also sine expression, which will give us J omega L. So this is the inductance with the impedance of the coil. This is simply the impedance of the inductor with respect to frequency. This is a complex number, which is an entirely imaginary number when there is only an inductor. But in real life, inductors will always have a series resistances along with them. So this cannot be purely inductive. Therefore, a realistic impedance of a speaker would be the sum of the real resistance of the speaker plus the inductance of the coil, omega L. But the impedance value you see in the manufacturer's data sheet or everywhere, probably the magnitude of this value, that means the magnitude of this impedance will be square root of R squared plus omega L squared. And it depends on the frequency of the waveform. And we know that the sound wave will always change frequency. Different frequency components will propagate through the coil at the same time. So this parameter is both responsible from the heating of the coil and the frequency response of the coil at the same time. So while designing a loudspeaker, these are the main and simplest electrical features to be taken into account. So that means high-pitched sound waves will see larger impedance, whereas the low-pitched sound waves will see a lower impedance on the coil. Therefore, the designed coil must exhibit an impedance magnitude between 4 or 8 ohms, because typical amplifiers require 4 or 8 ohms in the market, for both the high and low pitch sounds. Both should be in that margin. Otherwise, our coil can burn. I found the best amplifier to take up this task. This is a spatial tube amplifier that uses vacuum tubes to increase the power output of an electrical signal. It is generally used for guitars, but this time it will power up our coil. This is the 100% original replica of the unique amplifiers with thermionic valves used before the advent of transistor technology. But today they are still so popular because of the characteristics of the sound quality they provide for electric guitars. Just switching the clean channel, since we don't want any overdriven distortions in the sound waveform. That could be a great triumph for a rock concert, but not necessary in our situation. So here's around 30 turns of coil, which is connected to the amplifier, and the music is running, but nothing happens until I take a neodymium magnet like this and put it on the top of the coil. We start hearing music, and you can even see how the wire twists when the current passes through the wire and actually pushed back by the magnetic field. So force is applied by the magnetic field on the wire, which carries the current of the sound waves. The coil is vibrating between the magnet and the table, which creates the strokes of the sound. The size of the opening between the table and the magnet determines which frequency components will vibrate strongly, and since the distance is tiny, probably the high frequency components vibrating more, which is why the sound is squeaky a little, rather than being bass voices. So this is how a speaker works. Since the magnitude of the impedance will be slightly higher than this value, wire will not burn quickly and the amplifier can easily drive it. So let's test our coil's performance with more chaotic music with various frequency components. So here's the HipHop music, and I just stick the microphone so closer to the magnet so that you can hear it clearly. But even without the microphone, it's very clear to hear. Look at that, how wired to it is. It's awesome. And I can volume up further. Holy cow. So I have to be careful. If I volume up way too much, I might burn the coil. So it has been working for over 6 or 7 minutes and it's still working. Flying colors. Unbelievable. You can even hear the bass sounds. That's awesome. And when we remove the magnet, the sound will all... It's so hot. The cable just loosened up. But we can still hear the music. It plays from somewhere else. Probably in the amplifier or something. Connected another coil to this oscilloscope to see exactly the sound waves on the screen, and you see how different frequency components are included in the sound wave. It's so chaotic. Also, it actually radiates an electromagnetic waves, and I can actually catch them and screen on the oscilloscope. How beautiful it is. And if I get it closer to the magnet, look at that, I can still catch the sound actually, but nothing can be hearable. Whoa, interesting. Oh, I can still catch. I actually don't need the coil. Look at that. It is so weird. AC is so weird. The signals are so weird. Because I have a capacitance between the props probably, and that counts the electromagnetic fields. Yes. Shouldn't go too close. Yeah. You see how different frequency components are included in the signal. The coil can be improved further by increasing the thickness of the wire and number of turns. Our success depends not only the weight and thickness of the wire, but also depends on the cavity formed between the magnet and the coil. It is free to move sideways, but not completely free in the vertical direction. So we confine the vibrations in a thin cavity and let the coil vibrate and hit the magnet and the surface of the table to sound louder. Our coil got heated enough to almost burn my finger. That means the wire thickness is a little bit less than the required level. Thicker wires would perform better provided that more turns are added to the inductor to compensate the increase in the weight of the entire coil. But even with the current features, the coil may work for a long time. With more advanced techniques, it might even be possible to get better sound quality with no heating at all, but maybe at a later time.